Okay, so let's get started. So the topic is to introduce the OpenCL backend for Llama.cpp that is optimized for Qualcomm Adreno GPU. I'm from Qualcomm GPU architecture team. Been working on OpenCL for almost 15 years. So here's the agenda items. So I'll go through a quick intro to the team and what is Llama.cpp and why we work on Llama.cpp plus OpenCL. And a quick intro to the Llama.cpp workflow and the software architecture. And followed by our contributions to this project, including kernels, optimizations, and performance. And I'll talk about the status and the to-do list, a lot of work in progress, and the future work, and finally I'll summarize the talk. So again, I'm from the Qualcomm GPU research team. I primarily work on GPU and AI machine learning projects. So with a focus on architecture for GPU. We also participate in open source projects like TVM, MLC, and Llama.cpp. So we actually have two technical presentations for this IWOCL 2025. We have this one, and followed by next one is about TVM MLC for large language model. So we have been long-term contributors to IWOCL. We publish every year. We contribute some topics for last probably 5-6 years. So here are the contributors to the project. We is the main contributor, and he will on the high-level framework. And Alexander, Skyler, Sean, they all work on the kernel implementation optimization, including Shelby, who did a lot of experiment for the matrix multiplication kernels. Alex is my boss. He's really supportive for this project. So so people may ask, before we go to here, people may ask, oh, you're working on architecture, why you work on open source project, like a more software product? So the way we work is that actually, when we work on architecture, it's really use case driven. So we get customer use cases or benchmarks or some open source projects or some latest research topics. So we really study deeply into the use case, optimize them, and see where the bottleneck come from. Then we study architecture that we can enhance our architecture for future GPUs. So here's the resources and the references to the project. So we upstreamed the OpenCL backend to the Llama.cpp, so you can get the access all the kernels, through all of these links, how to build, And we also, we typically upstream some feature first to the Adreno, which is sponsored by Qualcomm. So then we merge to the mainline. We also publish a few blogs about this work. If you search for OpenCL, Llama.cpp, and Adreno, you will find out a few about this work. And finally, we have this OpenCL SDK and also programming guide in this place. If people are interested in how to optimize for Adreno GPU for OpenCL. So very quickly, an introduction to Llama.cpp. So this is an open source project written in C++ for inference of large language models. So it's inspired by the Meta's Llama work. So the quote from the Llama.cpp front page. So it's really to enable large language model inference with minimum setup. So it says locally and in the cloud. So I think for us, for Qualcomm, we really care the edge devices. So it's really to run your models on the local device. So this project supports a lot of models. I think most hygiene face models are supported by Llama.cpp. It's mainly for text generation, but it also supports multimodal stuff. through Llama. So in this project, there are a lot of backends currently. Actually, there has FUDA support. Used to have OpenCL backend based on CL Blast, and also Metal API, Vulkan, SYCL, and I think also this I listed this table, right? So there's Blast, Liz, and also the Huawei contributed to some of the backend to run Llama.cpp on their NPU, and ARM actually contributed some assembly optimized CPU code to the project. Llama.cpp also runs on Android, Linux, Mac OS, Windows, including Windows Snapdragon. Yeah, so it's quite a popular project. Yeah. So why we work on Llama.cpp? So it's really down to simplicity, flexibility. So it's really easy to work with. So written in C++, you can do whatever changes you like. You can upload your handwritten optimized kernels. You can. It has cross-platform support. Can be easily built on again Android, all these platforms through CMake with minimum dependencies. Very active, very popular project. Just checked yesterday. As 77,000 stars at GitHub. Supported by major GPU players like AMD, ARM, Intel, Huawei. And the performance, it's pretty decent actually. If you look at the numbers people reported, especially on the Apple platform, they really get a good decoding performance based on the reach the memory bandwidth peak, kind of very close to the peak performance, theoretical peak. So why OpenCL? So Ben and others already talked about it. So OpenCL is really a mature API supported by major GPU vendors, or easy to program, debug, profile. Especially for mobile and embedded system, actually OpenCL is very popular because of the really low level API that allow you to customize, to optimize to the level that maybe other API cannot reach easily. And for Snapdragon, Qualcomm Snapdragon SoC, we basically support OpenCL across all the tiers. For people who don't know, Qualcomm probably most famous for modem or this premium SoCs for Android smartphones, but actually we have a lot of other small, like low tier, really middle to low tier products that runs on Snapdragon. So we have IoT products, some robot actually powered by Qualcomm SoC. And a lot of actually the GPU code name, actually, I don't know. It's really we typically see like a premium tier, like an Adreno 740. We sometimes see like 710 or 705. I have to check what the spec that is. So there are a lot of small low tier devices. For this kind of devices, GPU is often idle or underutilized. A lot of these devices, you may not have any rendering task at all. So GPU, it's free for you. So as I said, Llama.cpp used to have an OpenCL backend. It's really based on the CL Blast. For people who don't know, CL Blast is actually a well-written benchmark that was published like 4 or 5 years ago. For Llama.cpp, the matrix multiplication is offloaded to GPU via CL Blast for the OpenCL backend. The kernels are not highly optimized for GPUs like mobile GPUs. I think they mostly optimized for desktop GPUs. It's actually deprecated later last year because of a lack of support or maintenance. So how we started this project, really brief history. So we started as a single person project. Early last year, our team member Lee actually started, playing with it. We gradually see that there's, gradually see more tractions coming from customers, internal customers, external customers. And as I said, yeah, so we actually get a customer from IoT, automobile, embedded, and compute, Windows on Snapdragon. So think of this this way. You probably heard like 7B model of like 30 billion model or something. So this model are huge. In reality, you don't probably need this such such large models on your local device. You can run very small models on your low-end device. Like we get a request from like a 1 billion model, even 500 million model. So these use cases are really like targeting very specific use case, not just generic like a question answers kind of stuff. But like one use case, for example, you can think of like, oh, this supermarket has this like a handheld device that you can actually ask questions. I want to buy something. I have allergy to some material. Can you suggest something, some products? Then they give you a list of the products. So this kind of use case is becoming really popular now. So from our side. So our goal for this project is to have an OpenCL backend well optimized for Adreno GPU. So it can be easily extended to other vendors' GPUs. So give a really high level, really quick like overview of the workflow. So Llama.cpp has lots of tools, including the conversion tool that can convert Hugging Face models to the GGML format, and they have this quantization tool which can convert like a AP16 models into like a Q4 format, and then through all these steps you can produce, you can have an executable that consume the converted format, the Q40 format. The software, really high level software architecture. So this is so-called Leap Llama, which handles a lot of this high level stuff, including model loader, graph composer, tokenizer, quantizer. And underneath there's this GGML, which handles tensor, ops, graph, and the CPU runtime. And in the backend, you will have this, OpenCL runtime depends on the API. You have OpenCL runtime or other metal runtime. And yes, you have this kernels, OpenCL kernels or metal kernels, so on and so forth. So here's a summary of our contribution to the Llama.cpp project. So as I said, we have a completely new OpenCL backend upstreamed to this project. We contributed like more than 50 kernels, including host code. We did a lot of debug optimization work. So right now, primarily we support the Q40 quantization format. As I said, yeah, the performance is tuned for mostly the premium Adreno GPUs, Adreno 700, 800. So the product you can look at Snapdragon Gen 123, Elite, X Elite. Some of running on Windows on Snapdragon. So we also kind of again IoT device. This we usually like the premium device that it used to be like 3 years ago. We kind of downgraded into like this low tier device. So we now trying to port this work into some really old GPUs, Adreno 600 GPUs. For example, this Qualcomm robotics kit. The optimization is ongoing. So we also have the options to allow customer to select different versions of kernels. Some models actually more sensitive to precision issues than the other. So it's actually a big topic. Yeah, we also have an internal version actually we developed using inline assembly, which reached a really high ALU utilization, but we can't expose because of the IP issue. So we need some extensions like a cooperative matrix from the OpenCL working group to in order to expose it. So just here's a list of the optimizations we used in the project. So just really high level few things. For example, on host side, we try to minimize data movement, better improve the memory management, use vector type. For Adreno, or specifically, we prefer image over buffer, and we tuned a lot of parameters. We use constant memory a lot. We also use subgroup functions, like broadcast functions for the matrix multiplication, vector multiplication kernels. We tried all different ways to get the optimal performance. Again, if you wanted to look at how to optimize on Adreno, yeah, this is the reference. I shamelessly promote this because this is written by me. So, yeah. So today, this backend supported a lot of models. So if you look at the list, yeah, we basically support all the popular models, including the latest, greatest, like DeepSeek DSTL model, Llama 2, 3, 7B, 3B models, Q1 and Microsoft 5 models, Mistral models, Llama models. So this is definitely not a complete list. Some of the, yeah, actually for DeepSeek, for example, so when after we upstream the work, like in November or December timeframe, we are done. We are mostly done with that, that stage. And then like DeepSeek came out in January. And we got the management ask, oh, can you run DeepSeek? And do you need to, add ops to DeepSeek to support DeepSeek? We actually we tried DeepSeek. It works out of the box. So nothing we have to do. So all ops just works perfectly fine with decent performance. So this is the beauty of open source. This project, all the top level stuff handled by the community. You just take care of all the key ops kernels, optimize them well. That's all you need. So we do see some models actually like this 5.4 model that we have to add something special in order to make the performance. But overall, yeah. So once we upstream this thing, most models work really well. So people will ask, can you run like even larger models? So for mobile devices, again, I said actually the trend is to run really small models. We internally we try like a 7B model or even 13B model, which work fine. But this model in reality, mobile devices, this memory is, consumption, the power consumption is really top priority. So most likely they will run like really small models, and these models could be sit in the devices, like as a personal assistant or something like all running all the time, or maybe even multiple models can run concurrently. So again, our focus is really the smaller models today. Just give you a really quick idea of how to measure the performance of large language model. So there are two things. So in this attention block, in this attention-based model, so there's so-called encoder and decoder. So this term, like sometimes you see prefill, prompt processing, all this encoding, all this are the same. Basically, it means how fast you can get the first token after you enter the prompt, the question. And the second metric is called decoder and token generation. This is really how fast how many tokens you can generate per second after the first token. So but both of them is higher better, like token per second. So give example, right? So yeah, if you have two examples here, and so for encoder, this is very important when you have like a long prompt use cases. The performance usually like with more inputs, with more token inputs, the performance will slow down quite a bit. This is why, because this is really a compute bound use case. So a lot of matrix multiplications have to be done for the encoder processing. For decoder, on the other hand, is it's mostly memory bandwidth limited. Think of like a 7-bit model. If you quantized to like 4 bits per each weight, you basically get like a 3 GB or something like 3.5 GB data. So this you for mobile devices where you have like a 60 GB bandwidth, the peak performance would be 17 tokens per second. That's theoretical peak. So which you can't really go beyond that. So here's the performance of selective models. So if you look at the so we have 7B. This really for the decoder we reach really high memory bandwidth. For the prefill, it's also quite decent. So you think of like if you have an input size of like 100 words, 100 tokens, you can get the answer within 1 second, which is pretty fast. Yeah. So these are the again I gave 3 devices. These are the Windows on Snapdragon. This is Snapdragon X Elite, and this is the second one is Adreno A30, which powers the Samsung Galaxy S25. 750 is powers the S24. Yeah, these are the premium Adreno devices. So here are the 2 again key kernels. I put a link to these 2 kernels to tell me if I want to go details. But basically, for the decoder, for the encoder, the bottleneck is the matrix multiplication. So the optimization is really how to improve the area utilization. So we list a few things here. For the more detail, you can check the kernel. The kernel really looks simple, but there's actually a lot of work behind. So for the token generation, it's also it's a try to maximize the bandwidth utilization. So we have very special ways to do that. We actually use some subgroup functions to better reduce to improve the locality, reduce the to improve the performance. So some discussions. So quality. This is also a very important topic. There's this prophylaxis score people usually use to measure how good your output is. The smaller number, the better quality. So there's a lot of tests over there. And there's also different benchmarks that people can use. For example, this Math 500 benchmark. One thing we did is to check the quality between CPU and GPU, which turns out to be closely matching. So for example, this you get 83%, really closely matching the CPU reference. And for the OpenCL version features, this work requires OpenCL 2, requires some feature like subgroup support. And some for the Adreno optimized kernels, we require some like this Qualcomm extensions. So we could port to OpenCL 1.x without subgroups, but that's to be still under discussion. So for the data type quantization precision, as I mentioned, the some models are very sensitive, more sensitive to precisions than the others. So sometimes we have to switch from LP16 kernels to LP32 in order to maintain the quality. This thing really become more important when the model becomes smaller. So like a 1 billion model, half billion model are more sensitive than the large models. In future we plan to do more like a dynamic kernel selection. So FP, like for example, some of the kernels like when you don't have FP16 genome support, you actually get the poor results. So this is also very important. So we participate in the open source project. We have some experience. So this is really for this project, this really big community support, very active project. So the framework is pretty mature and lots of functionality features. That's a good thing. On downside, sometimes it's really not really flexible to change to add some features, and especially on the debugger side, some also kernel fusion side, it's a little bit tricky to do things. For OpenCL standard, we found mostly work really fine. No much new requests, except we have this missing CL flow support for the read image H function, which we proposed to the working group. And we also, again, as I said, we have some internal version that actually almost double the encoding performance, but we have no way to expose today because of missing of this extension support. So ongoing effort and plans for this project, multiple things in the to-do list. So OLAMA is actually also a very popular project. For people who don't know, if you search OLAMA, maybe the stars is even more than Llama. So we also work on this. So right now, this Llama project doesn't have the OpenCL support. So it requires some like glue logic, some like hookup between Llama framework and OpenCL. So Adreno is really a tool, or you can think of a wrapper that makes the deployment of large language Llama.cpp a lot easier for different platforms. So to-do list, there are a lot of things happening in the large language model area. So this multi-model support is also is a direction, and stable diffusion, all this transformer-based stuff. Now, a lot of you probably heard like traditional CL-based models networks are moving to transformer-based. So this is one thing we are looking at. So for other features, algorithm level, API level, we have this flash attention, dynamic quantization, some int8, dynamic quantization support, dynamic kernel selection, and this mixture of experts. We plan to support, and also Metal and CUDA have better support in terms of features. We will look at what we are missing in the future. So the extensions, so OpenCL extension, like all these extensions are, we plan to add into the Llama.cpp project. So at this time, we haven't really done much. I forgot to mention, we are a really small team. The people who are listed to work on it, they have a lot of other work to do. So it's really a side project. Other topics. So again, I said, so we needed to think of how this co-operative matrix extension push forward. And one question I got is why you guys work on OpenCL instead of just optimize Vulkan kernels or Vulkan backend for Adreno. Vulkan is really not for. Vulkan has this Vulkan compute, but the Vulkan API itself is not for beginners of GPU developers. So it's really tricky to use, especially for the low-end devices. OpenCL is much easier to use than Vulkan. So really sorry to little bit 3 minutes over. Really quickly, we have another talk today that is MLC-based large language model. So people may ask, oh, you have two projects or two open source projects, or better, these two projects are all under my team. So why you work on these two different things? So they serve different purpose. So the MLC-based is all kind of the AI compiler, like I said, a lot higher than Llama.cpp, like an OpenCL layer. It's basically try to auto-generate a lot of kernels without intervention of developers, and to tune the kernels automatically. Also provide an option to plug in our hand-optimized libraries like CML. There's pros and cons for each approach, but we provided the option to developers, to customers. So again, just quickly, our contribution, we have a new OpenCL backend to Llama.cpp. Feel free to try it yourself. So we're optimized for high-end Adreno GPUs, and a lot of features are in plan. So again, we're a small team. We really can't do a lot of things, in short period of time. If you are interested, welcome your contributions. So final words, if you are interested in this project, go ahead, welcome comments, and welcome you contribute to optimize kernel or add to some optimized kernel for other GPUs. Feel free. So it's a great opportunity for the community to demonstrate OpenCL's capability and the potentials, to see that OpenCL is still strong. Yeah, that's all from me. Sorry to 5 minutes more.
Thank you.
Yeah. Any questions?
I wanted to ask two questions. So first of all, you have mentioned that OpenCL backend was deprecated, but I'm assuming it's not the case anymore with Qualcomm.
Yeah, with our contribution, yes, it's alive. Yeah, back to life. Yes.
Okay, thank you. And the second question, which you briefly covered, because you have mentioned the several key points of OpenCL backend advantages, but I'm curious about relative advantages, which you see, for example, OpenCL backend, which you have selected over, for example, SYCL backend or Vulkan backend, which you already briefly touched.
Yeah, so I'm a super fan of OpenCL. I work on OpenCL for 15 years, so I always try to promote OpenCL. So for mobile devices, I think OpenCL has its advantage versus SYCL or other high-level languages relatively. Because for mobile, the performance really we want to squeeze performance as much as we can. So we don't want to leave anything, there. So for SYCL, I think my personal opinion is that maybe you single source, you can get a quick deployment with the minimum effort. You don't have to chase the performance to the really low level. That's good for SYCL. For embedded, for low tier, OpenCL is the way to go. For Vulkan, as I said, right? So Vulkan is really not for people who don't have much graphics experience. It's really a tricky API. So so I think the bar to optimize Vulkan kernels or optimize Vulkan APIs is a lot higher than working with OpenCL.
So just to summarize, you have wanted something more low level than SYCL, but not as low level as Vulkan.
I would say it's Vulkan. It's not in terms of level. I think it's pretty much similar level. Vulkan, you can always go to the silicon, really a lot of optimization. But the Vulkan itself, the purpose, right? So it's trying to get rid of this driver overhead. You have to know what you're doing when you set up the host, like a lot of parameters. It's tricky. So, but if you know Vulkan well, that's I don't think you would see much difference between OpenCL and Vulkan. It's just again for the bar to work on with the mobile device. I think OpenCL is a lot easier. Yeah.
Okay, thank you.
Last question.
Hi, thanks for the talk. You showed that Qualcomm chips have int8 dot product support, which is fantastic. Do they have hardware support for matrix multiplication specifically beyond the dot product, like a systolic array, for example?
So today, the matrix multiplication kernel is really there's no special hardware. It's purely based on the regular ALU. But in future we could have. So that's all I can tell. Yeah.
No more question. I think we are almost ready for lunch. Thanks again.
Thank you. Very well.